Good morning friends. This is my second lecture on surface chemistry. Today I want to tell you the topic on Langmuir adsorption isotherm. The scientist who Langmuir proposed this theory on 1916. He proposed this theory on the adsorption of a gas on the solid. Okay. He made some assumption, that is the relation between the x by m, that is the amount of gas adsorbed, that is x by m versus pressure P. Okay. First assumption is the adsorbed molecules on the surface is of unimolecular thickness. This is the first assumption. Second one is the adsorption is the dynamic process. It is the dynamic process which consists of two opposing themes. That is, first one is condensation of the molecules on the surface of the solid, and second one is the evaporation of the molecules on the surface of the solid. This is the two opposing processes. Okay. Third one assumption is the condensation and evaporation, that is the equilibrium process. That is equilibrium process, that is what? Condensation and evaporation. Okay. Let us start the derivation of the Langmuir adsorption isotherm. Rate of adsorption directly proportion to the bare area into pressure. Bare area, it is the unavailable surface. Okay. Molecules are not visible, that is bare area. Next one is 1 minus theta, it is the bare area. Next, theta is the fraction of the molecules area covered by the gas molecule. Okay, that is theta. Then P is the pressure. For this, what we are writing here, rate of adsorption is directly proportional to 1 minus theta into P. That is, for this proportional, what we are taking here, K1. K1, it is the proportionality constant. Okay, that is equal to K1 into 1 minus theta, that is P. This is the first equation for this derivation. Next one is the rate of desorption. That is, rate of desorption is directly proportional to theta. Rate of desorption for this proportionality, what we are taking here, K2. K2, it is the constant, K2 into theta. This is the second equation. At equilibrium, what we are assumption is our, that is the equilibrium condensation and evaporation. That is, rate of adsorption is equal to rate of desorption. What is rate of adsorption? Rate of adsorption is K1 into 1 minus theta into P. That is the rate of adsorption. Okay. Rate of desorption, that is second equation, that is K2 theta. Okay. K1 into 1 minus theta P equal to K2 theta. What we are doing here? Multiplication. What? K1 P minus K1 theta P equal to K2 P. This is the multiplication of these two. Next, K1 P equal to K2 theta plus K1 theta P. What we are taking here? Theta is common. For this, theta is a common. K2 plus K1 P, it is in bracket, then theta is outside. What we are taking here? Theta is equal to K1 P divided by K2 plus K1 P. This is our third equation. We know that the amount of gas adsorbed per gram of the absorbent is directly proportional to theta. So, we are getting here x by m. It is the amount of gas adsorbed per gram of the adsorbed is directly proportional to theta. That next equation is x by m. For this intermediate, what we are taking here? K3. K3, it is the proportionality constant. K3 theta. Putting the value of theta in the equation 4. Theta, it is the equation, third equation. Putting here the equation 4. What we are getting? X by m equal to K3 K1 P divided by K1 P plus K2. Dividing this equation from numerator and denominator by K2. So, what we are taking? X by m equal to K3 K1 P divided by K2 and K1 P divided by K2 and plus K2 divided by K2, that is K2 is cancelled. For what we are taking? 1. So, next equation is, that is x by m equal to AP by BP plus 1. So, what A and B are the constants, where A equal to what we are taking here? K3 K1 divided by P, it is the A. K1 K3 divided by K2, it is the A, and B is the K1 divided by K2. This is the our final equation for Langmuir adsorption isotherm. The relative between the x by m, that is the amount of gas adsorbed versus pressure. For this, what we are taking next? At low pressure, what At low pressure, the Langmuir adsorption isotherm is x by m equal to AP divided by BP plus 1. At low pressure, the term BP can be neglected as compared to 1. Next, what we are taking, that equation is x by m equal to AP. This is the equation 6. Next, at high pressure, x by m, that is the Langmuir adsorption isotherm equation is x by m equal to AP divided by BP plus 1. At high pressure, 1 is neglected as compared to BP. So, the equation is x by m. Here P is cancelled. Next, what we are taking, x by m equal to AB by B, that is the constant. This is 7th equation. From at low high pressure and at high pressure, the intermediate pressure is from equation 6th and 7th, what we are taking, x by m equal to AB by P naught, that is fraction. From these equations, that is at low pressure, at high pressure and at intermediate pressure, what we are consider, it is clear that the pressure increases from low to high. Pressure increases from low to high, then the power, the value of P is decreases from 1 to 0. That is here, see here P value is 1, but from at high pressure, what we are getting, here P is neglecting. So, what we are considering, that when the pressure increases from low to high, then the value of the power of P is decreases from 1 to 0. Then at intermediate pressure, the fraction is, the power of P is fraction, that is x by m equal to AB into P raised to 1 by n, where 1 by n is the fraction, that is 0 is smaller than 1 by n, then smaller than 1, that x by m equal to constant into P raised to 1 by n, where the final equation is x by m equal to, that constant is k into P raised to 1 by m. This is 8th equation. This is all about our Langmuir adsorption isotherm derivation. Thank you.